Chapter 12c, we're talking about transition matrices and their applications. Now, if we look at this transition matrix down here, you'll notice it does look very similar to a network diagram, and essentially it is. The main difference is that they have percentages, and the corresponding transition matrix turns those percentages into decimals. Now, that's very important. In a transition matrix, they need to be represented as decimals, not percentages. So throughout Chapter 12c, we're going to be looking at this example of two rental car companies, one in Bendigo and one in Colac. And we're going to be coming back to this example a couple of times throughout the 12c chapter. So looking at this diagram, we can see that, and we've also got this information laid out here, if a car gets hired in Bendigo, 80% of those cars that get hired in Bendigo will be returned to Bendigo the next week. So you can see here, also correlating to the transition matrix, a car that's rented in Bendigo, 80% of the time, so 0.8 as a decimal, it is returned to Bendigo. And we can see that if 80% are returned to Bendigo, that leaves 20% to get returned to Colac. Now, you should understand that the 80% plus 20%, that has to equal 100%. If only 10% were returned to Colac, then we're missing 10% of the cars. Or if more than 20%, then we've gained cars. So there's the two arrows coming out of Bendigo have to sum to 100%. And similarly, we see that 90% of cars hired in Colac are returned to Colac. That leaves only 10% of cars to be returned to Bendigo. And we can see that shown here. Rented in Colac and returned to Bendigo, 0.1, which is our 10%. Rented in Colac, returned to Colac here, that's our 90%. Now, just as these percentages have to add to 100%, that corresponds to the columns of a transition matrix summing to 1. So we see here the important note is that the columns of a transition matrix need to add to 1. Now let's go through a quick example here. We're going to stick with the rental car company analogy, but this time we've got 3 different branches. We've got Albury, Wodonga, and Benalla. And this is slightly more complicated. Now, to fill in our transition matrix using this transition diagram, we're just going to go element by element, filling them in. So if a car is rented in Albury and returned to Albury, we're looking at this first element here. So what we're going to look at our diagram is we're going to look at the arrow that goes from Albury to Albury. So it's this loop here. And we see it's 70%. So 70% as a decimal is 0.7. Now, just to remind you, to convert a percentage to a decimal, you're just dividing it by 100. So 0.7. Now, if you are renting the car in Wodonga and returning it to Albury, we're looking at this second element in row 1, and we're going to follow the arrow from Wodonga to Albury. So this arrow here, they're pointing from Wodonga to Albury, and it's 5%. Now, if you divide 5 by 100, we get 0.05. So 5% as a decimal, 0.05. And finally, the third element in row 1 is when you're renting in Benalla and returning to Albury. So we're going to check the arrow that flows from Benalla to Albury, and that's 12%. And you can go through and fill out all the rest of the elements there. All right, so we've finished filling them in, and you'll notice that keeping in line with this fact that the columns do need to add to 1, I'm not going to do it on the calculator, but if you did want to double check, you should find that each of these three columns do add to exactly 1. We're going to quickly look at a past example about interpreting these transition diagrams. So we've got 3 candidates in an election: Mrs. A, Mr. B, and Mr. C. Voters' preferences can change with the transition diagram shown here, showing the percentage of voters who are expected to change each month. First part of this question asks us, of the voters who preferred Mr. C this month, what percentage are expected to prefer Mrs. A next month? So what we're looking at here, the voters that preferred C this month, and we're looking at the percentage of those who are expected to prefer A next month. So what you're asking yourself here, you're going from C to A. So we're looking at the arrow that points from C to A. And you can see it's this arrow here pointing this way. It's 20%. So we know that 20% of the voters who prefer Mr. C this month will prefer Miss A next month. The second part of the question says that this month there are 2,500 voters who preferred Mr. B. So we're looking at Mr. B for now. How many of those voters will still prefer Mr. B next month? So we're looking at from B this month to B next month. So we're looking at the loop that goes from B to B, and we see it's 80%. So we know that 80% of those 2,500 voters will prefer Mr. B next month. Now, the way I like to think of percentages of a whole number is I'll get a fraction. So I'm thinking 80%. And I think, so per means divide and cent means 100. So when I think 80%, it's 80 divided by 100 of, we multiply by the full number. So 80% of 2,500 is 2,000. So next month, we're expecting 2,000 people to prefer Mr. B. Next up, we're looking at transition matrix recursion, which is where we're making predictions with these transition matrices. So we're going to continue looking at the rental car problem. Let's say that the company buys 90 new cars. They put 50 in Bendigo and 40 in Colac. So because not every car that gets rented in Bendigo gets returned to Bendigo, only 80% get returned to Bendigo and 20% get returned to Colac. We did that earlier with the transition diagram. So obviously, a question that the manager is probably going to want to ask is where or how many cars are they going to be at each location after 1 week, after 2 weeks, after 3 weeks, and so on. So this is where we're going to use the transition matrix to make predictions. And what we begin with is the initial state matrix, and that's shown with S naught, so S with a subscripted 0. So we're starting. The first row of this column matrix is 50 because that's the number of cars that are in Bendigo. And the second element in the column is 40 because that's the number of cars that are in Colac. Now, a question you might be asking is, well, why is it not 40 and then 50? Why does it go Bendigo first and then Colac second? If we think back to how we actually created our transition diagram, see how we've got Bendigo as the first row for the returned to and Colac as the second. We've got Bendigo as our first column and Colac as our second column. So it only makes sense that in our initial state matrix, the number of cars at Bendigo goes first and then Colac. So if S0 is our initial state matrix, then what we're going to say is that S1 represents the state or where the cars, which of the two branches the cars are at after 1 week. And the way we calculate it is S1 is equal to our transition matrix multiplied by the initial state matrix. So remember, that's the transition matrix that we got from our transition diagram. So we multiply that by our initial state matrix, and what we get out, if we were to, you could either do it by hand because it's not a very big calculation, or you could put it into your calculator. You would end up with 44 and 46. So because we know 44, the first element represents the cars in Bendigo, we know that after 1 week, there are 44 cars in Bendigo, and there's 46 cars in Colac. If we want to find out how many are at each location after 2 weeks, we have S2 is equal to the same transition matrix. So the transition matrix doesn't change, but instead of multiplying it by S0, which is the initial state matrix, we just multiply it by the previous week, or the previous state matrix, which is S1. So we multiply it by this matrix, 46 and 44. And what we got out is, there's decimals there, but rounding to the nearest number, you would say that there is 39 cars at 39 cars in Bendigo and 50 cars at Colac. In fact, I've just realised that those two numbers need to sum to 90 because we're not adding or removing any cars here. So these two numbers have to add to 90 because there are 90 cars total. So that should have actually been 51. So there's 39 cars at Bendigo and 51 cars in Colac. What you might notice here, that say if we wanted to find S3, we would do S3 is equal to T multiplied by S2. And that's the pattern that's happening. So you might remember from financial maths that what's happening here is a recurrence relation. And we're going to think back to chapter 8b. A recurrence relation contains a starting point, so V0 or V0 equals 3, and we've got a rule. Vn plus 1 equals Vn might be plus 5. That's just an example. So we've got something similar here. We've got a starting point, an initial state matrix, and we've got a rule. And that rule takes the general form of this. So this is our recurrence relation. We've got S0 as our initial state matrix, and Sn plus 1 is equal to T multiplied by Sn. So that's how we get the next one. Now, that's all well and good, but I think an even more powerful rule, and the one that you should try to aim to use more often, is this rule. So you can skip straight to whichever step you want just by raising the transition matrix to the power and multiplying it by the initial state matrix. See, when we did this, to get to S2, we had to do two separate calculations. We had to do it sort of twice to sort of go through each step. Whereas if you use this rule, you could have skipped straight to it. So we'll do some examples on how this recurrence relation will work. We're going to look at a different scenario. We've got a factory that has 80 working machines and there's 20 broken ones. On average, it's found that each month, 15% of the working machines will break and 5% of the broken machines get fixed. First thing I want to do is to find the transition matrix. So because the machines can be in two different states, they can either be working or broken, we know that the transition matrix will be a 2 by 2 matrix. So say we've got this month a machine is working or broken, and next month the machine is working or broken. So let's start here. So what percentage of machines that are working this month and will also be working next month? Well, if 15% of the working machines break, what we have left over is 85. So there's 85%, which is 0.85. 85% of working machines this month will continue working. And we know that this one will be 0.15 because 15% of working machines this month will then be broken next month. We also know that 5% of broken machines get fixed. So machines that are broken this month, 5% of them will be working. And what we're going to have left over, if we take the difference between 100% and 5%, we've got 95% left over. So 95% of broken machines will stay broken next month. Part 2 of this question asks, how many working and broken machines will there be after 1 month? Well, we can use the rule for the state matrix after n steps. So we're going to use this rule. Now we've already got t, we just need to figure out what is S0 or S0. Right, so we got a 2 by 2 matrix here. Now S0, remember, it is the initial state. So from the question, it actually tells us that we start off with 80 working machines and 20 machines that are broken. So because we've got working then broken as our sort of order here, or reading left to right, working then broken, we've got our 80 working machines in the first row and 20 broken machines in the second row. Now all we need to do is plug the numbers into the formula. So we're trying to find how many working and broken machines after 1 month. So we're trying to find S1. So we're going to raise the transition matrix to the power of 1 and then multiply it by our initial state matrix. So we can do that in our calculator. So we'll enter the values in. I'm going to name that T. And then we'll get S. Might name that S0. So now we want to find S1, which is just T multiplied by S0. All right. So we've got S1 is equal to 69 and 31. So there are 69 working machines and 31 broken machines. And the third part of the question asks us, how many working and broken machines will there be after 1 year? Well, we know there are 12 months in a year, so we want to find S12. That's what we're trying to find. And again, we're just going to use this rule. So S12 will be T to the power of 12 multiplied by the initial state matrix. And because I've already assigned T and my S0 in here, doing that is going to save me a lot of time. So I've got T to the power of 12 multiplied by S0. I'll round to 3 significant figures. So I've got 28.8 and 71.2 at the bottom. So what that translates to is we've got 29 working and 71 broken machines.